Welcome to Demystifying Math. In this lesson, we're going to be discussing inverse functions. An inverse function undoes the operations that were done onto x. If two functions are inverses of each other, then when we compose them in either direction, we should get x. Two functions are inverses of each other if and only if every point a, b on one function there occurs a point BA on the other function. For example, if our function f of x is x minus 3, then to undo the operation of subtracting 3, we would add 3. So our inverse function would be x plus 3. Notice that if we compose the two functions, we get x. And if we do it in either direction, we still get x. Notice also that we have these points on the f of x function, 1 and negative 2, 2, negative 1, and 3, 0. If we reverse the order of pairs, they should satisfy the inverse function. So if I plug negative 2 into g of x, I get out positive 1. If I plug in negative 1 for x, I get 2 for y. If I plug in 0, I get out 3. To find the inverse of a function, we will simply undo the operations that were done on x. With this function, x is multiplied by 5 and then subtracted 8. To undo those operations, we're going to do it in the reverse order with the opposite signs, or the inverse functions. So we're going to start by adding 8 and then dividing by 5. There is a simple way to do this. You simply are going to exchange x for y and then isolate y. So we're going to start by letting f of x equal y, and then replace x with y. And now we're going to isolate y. So I added 8 to both sides, and now I'm going to divide by 5. So I have 1/5 x plus 8/5 is equal to y, which is going to be the inverse function. So I'm going to replace y with f to the negative 1 of x. If 1/5 x plus 8/5 is the inverse of 5x minus 8, then when I compose the two functions, I should get x. So we're going to start by putting the f to the negative 1, or the inverse function, inside the f of x function. So where I have an x in f of x, I replaced it with 1/5 x plus 8/5. Now I'm going to distribute the 5, so that's going to give me x plus 8, and then take away 8, and I get x. Now this should work in both directions if they're actually inverses of each other. So we're going to take the f of x function and put it in for x in the inverse function. So I replaced x with 5x minus 8. Now I'm going to distribute the 1/5, and that's going to give me x minus 8/5, and then adding the 8/5 gives me back to x. So this shows the two functions are inverses of each other. I graphed the two functions on a line. In this case on the graph it's showing that the inverse function is called g of x. But you can see that they are reflections of each other over the line y equals x, which is the h of x function on the graph. And you can also see that the ordered pairs are reversed. So on the f of x function we have an ordered pair of 3, 7. On the inverse function, 7, 3 is an ordered pair. 2, 2 is the point at which they intersect, which is on the line y equals x. You have other points at 0, negative 8 for the f of x function, and the corresponding point on the inverse function is negative 8, 0. Anytime that you have two functions that are inverses of each other, they should reflect each other over the line y equals x. If your function is not one-to-one, then you will need to restrict the domain so it is one-to-one in order to find the inverse of the function. If you don't do this, then the inverse of the function, when we flip it over the line y equals x, will not be a function itself. We want both the function and its inverse to be functions. So we're going to start with 4 over x squared. Notice that this is not a one-to-one function. It would be, however, if we restricted our domain. So if we have our domain be strictly greater than 0, we would only be taking the right side of the graph. And that part of the graph is 1 to 1. Now we can go ahead and proceed to find the inverse. Using our new domain and our same range that we had before, we're going to replace f of x with y, exchange x for y, then isolate y. So I multiplied both sides by y squared, and I'm going to divide by x. So y squared is equal to 4 over x. Now I'm just going to take the square root. Normally when we take the square root, we put a plus or minus sign out front. In this case, because we only kept the right side of the graph of the original function, we only need the positive part of the radical. And then I rationalize the function. So I have 2 squared roots x over x is going to be g of x on our graph. So you can see that these two graphs are reflections of each other over the line y equals x. They will have reverse ordered pairs as well, and they have the same domain and range. Okay, let's look at another one. In this case we have a quadratic function which graphs as a parabola. It's not 1 to 1. It won't pass a horizontal line test. So what we want to do is restrict the domain so that it will be 1 to 1, and then we can find the inverse of the function. So in this case our vertex is at 2, negative 1. If we just take the right side of the graph, our new domain will be from 2 to infinity, and our range will stay the same. You always want to try to keep the range the same when you restrict your domain. And then we'll have this side of the graph only, from 2 to infinity, and our range being from negative 1 to infinity. Now we can easily find the inverse of this function. So again, we're going to exchange x for y and isolate y. So I'm going to bring the 1 over to the other side and then divide by 4. And then I'm going to take the square root of both sides. And again, I only want the positive square root. And I'm going to simplify. The square root of 4 is 2. And then I'm going to bring my 2 over to the other side, so I'm isolating y. So that's going to be my inverse function. So I'm going to call it f to the negative 1 of x. The domain of this function is from negative 1 to infinity. So if they are inverses of each other, I can show that by composing them. So I'm going to take the inverse function and put it into the f of x function. So I have 2 plus the radical x plus 1 over 2, and then minus 2, and that whole thing is going to be squared. That's going to be multiplied by 4, and then I'm going to subtract 1. So notice that in the parentheses the 2's cancel out. Now if I take the square of the square root, those cancel each other. So I have x plus 1, and then I squared the 2 in the denominator, which is 4. Now the 4's cancel out, and I get x. So I've shown that the composition is x in one direction. Now we need to do it in the other direction. So we're going to take the f of x function and put it inside the inverse function for x. So I'm putting the 4 times x minus 2 all squared minus 1 under the radical and then adding 1 to it. So the 1's cancel out. Now instead of trying to FOIL out the x minus 2, I'm going to use the fact that the square root undoes the squaring. So the square root of 4 is 2, and the square root of x minus 2 squared is x minus 2. Now the 2 in the numerator and the 2 in the denominator cancel each other. So we just have 2 plus x minus 2, which gives us x. So we can say that those two are inverses of each other. Now when I go to graph them, you can see that they are reflections over the line y equals x. And you also see that the domain of one function became the range of the other one. And the range of the first function is the domain of the inverse function. Again, g of x is representing the inverse function. You can see your ordered pairs are exchanged. AB on one becomes BA on the other one. Notice if we had kept the entire parabola, it would not be reflections of each other, because you would have part of your graph going up over here. And you wouldn't have anything to reflect over here because it would not be in the domain of the radical. Keep that in mind when you're looking for your inverses. Thanks for tuning in to Demystifying Math.